The objective of this video is to introduce electric and mechanical angles and clarify harmonic components of magnetic and electric loading. So recently we've introduced a rather robust framework for considering the harmonics in our machines. We've been talking about the Fourier series decomposition of our spectral component and a phasor representation so that we can talk about any individual harmonic as a phasor of a cosine, and we can talk about the total signal as the summation of a bunch of cosines, each at a different frequency. And up until that point, we had already been discussing spectral components of our quantities. We've been talking about individual harmonics of our electric loading and our magnetic loading in order to derive our sizing equation. In order to come up with our expression for torque, we considered only the fundamental component of our magnetic loading and only the fundamental component of our electric loading. The point of this video is to bring that discussion back into our rather robust discussion of Fourier series. So we're going to talk about magnetic loading and electric loading independently. Let's begin with magnetic loading. And we've been describing magnetic loading with this expression. And there's two peculiarities about this expression for how it fits into our Fourier series analysis. The first is that we're using the subscript 1 when, in fact, alpha is being multiplied by p. So why does 1 match to p? And we'll be talking about that in a little bit. But before then, we're going to be talking about the peculiarity of why theta does not have a p in front of it. So basically, this magnetic loading expression is shifting our entire cosine waveform by the angle theta, which was our rotor's angle. And the question is, why doesn't theta have a p in front of it? And I'm going to tell you the answer right up front, and then we'll get to how that works out. And the answer is that theta in this expression is in units of electric radians. That is, theta is actually equal to p times our mechanical angle of our rotor. Let's sketch this out to show what I'm talking about here. And I'm going to draw this for a 4-pole wound field synchronous motor, a 4-pole salient rotor. And in this case, our rotor is rotated off the horizontal axis by theta mech degrees. And if we were to label north and south poles on here, they might be labeled something like this. So we can clearly see that this is a 4-pole rotor. And below that, let's sketch the magnetic field we'd ideally like to see. Let's sketch this expression right here, down below the rotor. So in an ideal world, where we have no harmonics, we'd have an air gap field that has 4 poles, so it repeats twice, and has a certain amplitude. And that air gap field is going to be rotated by theta mechanical radians. As our rotor rotates, the air gap field is going to move. And if we write that expression out down below, it's going to look something like this. So this is an expression for the normal field, the no-load field in our air gap of a 4-pole rotor as the rotor rotates by theta mechanical. We again have a mismatch here because we've got this theta up here where we've got theta mechanical down here. And so the reason for this is that, especially in motor drives, we like to talk about the rotor as being a 2-pole equivalent rotor. We notice that we have symmetry here. The waveform repeats itself after 180 degrees, so every pole pair, the magnetic field repeats. And so it's a little bit simpler to draw this just as a 2-pole rotor and then extend it up to however many pole pairs we have with scaling equations afterwards by scaling everything by the quantity p. And so the 2-pole rotor has all the necessary information that we need to study our motor. Because by definition of what it means to have periodicity by increasing the number of poles, we have all the information contained within a single pole pair of the machine, at least as far as the rotor is concerned. So this 2-pole structure here is just scaling 2 poles of our complete rotor. And this is something that comes up much more in electric drives contexts. In machine design, we sometimes alternate back and forth between the contexts. You'll see that in your textbook. It's easier to consider this as a general structure and then scale it up to however many poles you actually have. But in some contexts, you actually need to consider the machine in its true form as having 4 poles. So pay attention to this as you read your book and as you watch my lectures. Think about whether I'm presenting this as an equivalent 2-pole structure or the full multi-pole rotor. And when it's really important, I'll be pointing this out to you. Let's now go back to our equations and rewrite our magnetic loading in terms of the Fourier series format that we've been developing over the last couple of lectures. So the Fourier series for our waveform is this expression where we're noting that we're shifting it by theta mechanical as our rotor rotates. And we can zoom in on an individual harmonic until we get this form here. And then we can choose to write our expression specifically for n equals p. That is this case down here, or this case. And we note that in this case, I did not write any expression for phi n or phi p. That is, I left this out of our expression. The reason for that is that we've deliberately aligned our reference frame so that phi p equals 0. So by our choice of this angle and this location, we by default have phi p equals 0. And so there we have it. There is our magnetic loading in terms of its harmonic component at frequency p, at index p. And we are choosing either to express this in terms of electric radians, as we did up here, or in terms of mechanical radians, right here, we have to multiply it by p. So the remaining business is what is going on with this pesky 1 in our denominator. Why are we choosing to have an index 1 when we originally presented this, whereas right now we've written this with an index p? And the reason is that the way that harmonics are traditionally defined in electric machines. And so the convention in electric machines is to redefine the harmonic index as a multiple of our number of pole pairs. So that is to say that it's a harmonic of the electric frequency. And you can see that that's how we've written this out here. We've defined this variable v, which is equal to our true harmonic index of our Fourier series divided by the number of pole pairs we have. And remember, we just showed up here that the fundamental component in our air gap, the magnetic field that occurs at the frequency of our number of poles, is at harmonic index n equals p. So we redefine this in terms of variable v to be equal to 1. So when n is equal to p, v is equal to 1. We can see that from this expression. And so when you look at literature on machines, when you read this textbook, oftentimes everything will be referenced to the number of pole pairs. And so we've now rewritten our expression for the field in our air gap in terms of this variable v. And we can see that if we're talking about the fundamental, or the magnetic loading, that is at v equals 1, which then matches our expression up here and corresponds to this expression when we write it in terms of our index n. And we can construct a table showing the mapping of v and n. So consider a 4-pole machine. And you can see that with this definition, it's possible to have values of v that are less than 1. So right here, for example, for n equals 1, our harmonic v would be 1/2, and we call these subharmonics. And we like to pretend in our electric machines that all the harmonic content in our fields and in our voltages and currents are going to be harmonics of our number of pole pairs, harmonics of p. However, in practice, especially when we deal with fractional slot windings, we end up with subharmonics, which have a period less than our number of pole pairs. And so when we talk about all this, we will alternate between indexing based on n and indexing based on v. And you'll have to pick this up based on the context. When it's important, I will be sure to point it out to you in the videos. So this answers our two questions. Our questions were, why didn't theta have a p in front of it? And that's because we were dealing with theta in electrical radians. And our second question is, what is going on with this index 1? And that is because we are considering this in terms of the index v. So v equals 1, n equals p. And abstracting this way, taking v as the harmonic index of p, gives us a little bit more of a uniform way to look at machines independent of the number of pole pairs. We just talk about harmonics that occur at multiples of the number of pole pairs. And this will make a bit more sense when we get into the details of winding design and how we connect coils together to change winding factors. Okay, so I said first we're going to start with magnetic loading. Now we're going to address these same things with electric loading. And I'm noting down that for electric loading, we have a similar story for how we can talk about components as being either indexed to n or v, and we can talk about electric degrees or electric radians versus mechanical radians. So if you recall, we had said that in order to create torque, we need to have this rotating current density on the inner bore of our stator. And I'll write this out as a circumferential expression that we had developed. And similar to our magnetic loading, we had this pesky 1 hanging around, and then we had this angle here that wasn't multiplied by p. And again, exact same thing as before. This index 1 is in regards to mapping based on v, and this alpha w is in electric radians. And you can also see this based on how we had defined alpha w. Alpha w, in order to create a rotating torque, in order to create a torque for a rotating rotor, needed to be equal to our rotor's angle, which was theta, so it was in electric radians, plus some angular offset. And in order to create this rotating surface current, we talked about it in terms of a three-phase winding. And we've also mentioned in the past that this could be any phase, any number of phases greater than 1. So it could be a 2-phase winding, it could be a 4-phase, a 5-phase, a 6-phase. But for our purposes, the 3-phase winding is the most common, and so that's how we will continue to develop this. And as an aside note, the way we denote phases is with the variable m. So in this case, m equals 3. So our 3-phase winding expressions, we had written this out in terms of the fundamental as the following. And in these expressions, we had this A, C, pH hat. And we said that this is to distinguish the fact that we're talking about the equivalent current density of a single phase winding, whereas when you sum up all the current densities together, you get this final AC. So we had the pH to indicate that it was a single phase. And then we had this hat to indicate that it had been normalized by the amount of current. And we did this so that we could recognize that all 3 windings have the exact same distribution of turns, but they're just rotated by 2 pi by 3 from each other. And again, this 2 pi by 3 is an angle in electric degrees, or electric radians, and we will denote this as being the phase separation. So alpha pH, and we can also say that this is unique to each of these. So we have a negative 2 pi by 3 for phase V, and we have a negative 4 pi by 3 for phase W. And for phase U, alpha U is equal to 0. And so we had come up with a sketch for how these are distributed in the inner bore of the stator, and I'm going to reproduce that here. So our phase U winding is centered at 0 degrees off the horizontal, so I'm indicating alpha U there, and its conductors peak at plus and minus 90 degrees from there. So in the fundamental component, we have the most ampere turns up here and down here, and then the least ampere turns right at the axis. And phase V occurred 2 pi by 3 radians later. So the same winding, but just shifted 2 pi by 3. And phase W occurred 2 pi by 3 radians after phase V. Now, this again was drawn for an equivalent 2-pole machine. If we continue our example for a 4-pole machine, what we would actually have for a winding layout is the following. And you can see that the whole thing repeats itself twice. So compared to the 2-pole machine, the 4-pole machine has all the phase windings located 1/2 the distance from each other. So instead of 2 pi by 3 radians, the phase offset between the phase windings is now pi by 3. And you can generalize this to a p-pole pair machine by saying that it's going to be 2 pi by 3 divided by p. And so we have our full phase sequence over 180 degrees, and then we restart the process and have it again over the last 180 degrees. This makes sense because our number of pole pairs has doubled. So we're going from a magnetic field that looks like this to a magnetic field that repeats itself twice within one revolution of the inner bore of the stator. And we can write this out in our notation, in our Fourier series notation, as follows. So you can see here that phase V is separated from phase U by 2 pi by 3 divided by p. And we'll do this again for phase W. So phase V is assumed to be the exact same winding as phase U, just delayed 2 pi by 3 by p radians in the air gap, just shifted that many radians in the air gap. So it'll have the same coil sequence, but just shifted by 2 pi by 3 radians in the air gap. So that concludes this video. In summary, we've talked about harmonics and AC machines, and we've gone back to review our prior discussion on electric and magnetic loading, and then shown how this fits into our Fourier series framework for the spectral component of our air gap, flux density, and electric loading. And in doing this, we had to define electric and mechanical angles. We showed how it's common to take a rotor with an arbitrary number of poles and consider it as a 2-pole rotor, but in doing that we had to define this angle theta electrical, the rotor angle theta electrical, which is just scaled by the number of pole pairs. And it turns out that we can scale all the quantities by that way. So our inner bore of our equivalent stator has radians that are scaled by p as compared to the actual mechanical system, the physical system. So we talked about this in terms of our magnetic loading, and we showed how in electric machines it's common to define a new harmonic index V that's equal to our true harmonic index divided by our number of pole pairs, so that when we talk about quantities, harmonic quantities at index 1, that corresponds to the number of pole pairs of our machine. We then talked about electric loading and reviewed our equivalent surface current that rotates on the inner bore of our stator and how it is produced by multi-phase windings, and talked about how that also can be cast as an equivalent 2-pole machine or shown as the true p-pole pair machine, and then talked about how to write this in terms of Fourier series components. And this allows us to zoom in on any individual harmonics to write this as a single harmonic at a time if we choose to pick a particular value of n or of lowercase v.